This is the session that's extraction and semantics, and the first talk is going to be about ornaments, given by Pierre Dagand.
Thank you. So yes, ornaments, transporting functions across these things.
You're not switched on.
I'm not switched on.
No.
They should turn me on. You said they
Turn
would
it
turn me on.
Turn myself off.
Right. Thank you. So yes, functions and ornaments, or rather ornaments and transporting functions across it. So what are ornaments? So Connor alluded without saying it, but use a lot of ornaments in this morning presentation. So perhaps I should say right now that unlike Connor, I will not drop my pens today, right now. That would be embarrassing for me and for you. So I keep my pens over there. So ornaments are this story about data types and evolution of data types. So the standard, typical example of an ornament is natural numbers. Right? You have this data structure, but as a data structure, it's a linear object, right? Successor, 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 and then 0. So linear thing. And then the idea of an ornament, for example, what we call the list ornament, will take that structure, keep it, and then for every successor, it will add an element A, right? So it extends or ornaments natural numbers into lists. So that's not the whole theory behind ornaments, but that's all I will need in this talk. And if you want to know more about ornaments, Connor wrote a paper about that, which you should probably read then. So what you get from that is you can easily create new data types from old ones. So it's a very nice organization principle. Then you can start saying, you look at your library, and it's even more true when you're doing dependent types. You look at your library, and then you can start explaining where data types come from and how they merge into different things and became new things. So you know where they come from. But if you're an actual programmer, not an academic, but a programmer, you're not defining data types just because they are nice. We do that, but we are strange people. You define data types as a mean towards some end, and this end is writing functions, right? Computations. So let's say you have your library on natural numbers, and one of this function will be addition of natural numbers, right? And then you ornament natural numbers into lists, and you start needing some function onto lists. And one of them will be concatenation of lists, right? And if you look at this code for lists, concatenation append, the append on list, and the addition of numbers are pretty much similar, right? Also, when you are dealing with numbers, you wrote this subtraction function. And then you start moving to lists, and you need this function that does drop, that drops the prefix of some list. Right? And again, that's quite similar, although not the same, but it's very similar. And finally, and that will be our example, running example in this talk, is a comparison function where you take two numbers, and if, in a sense, if m is inbound with respect to n, then you say true. If it's not, then you say false, right? And then you implement your list objects, and there's this function in the list library which is lookup. If m is indexing something which is inbound, which is inside the length of the list, then you should return something. And if it's not, then you should return nothing. Right? So there seems to be a connection. Oh, and this is a new ornament for you. You can go from booleans to, you can ornament them to maybe, by saying when you used to say true, now you can say there is something, and that's this something. This is the A, right? So if you want ornaments, they capture this structure preserving transformation of one data type into a new one. And so because of our constructive object, they exactly tell you what is new in there, and by all this technology, you can create new data types very easily. That's all very nice. But then we need to kind of rationalize this diversity. And to do that, we invented function ornaments, so let's say you take the example of a comparison function. You would like to identify all functions on, say, lists, which are respecting the structure that is used by the comparison function. And for all those guys, you would like to be able to help the user take the comparison function, and say create the lookup function. So we like to help user do this transformation. So as here rationalize this diversity by say you have your date type, you ornament it to a new one. This date type has a bunch of library functions to it. You would like to transport them and just explain to the computer what is new when you're dealing with a list, which wasn't already there when you were dealing with natural numbers. So that's kind of the idea of this talk is to rationalize the diversity. In this talk, I'm going to focus on this comparison function, and what I want to do is implement the lookup. So, so as a programmer, I have already a library of natural numbers and comparison function. I just invented lists, and I would like to implement a function which, when given m, which is in the length, which points into somewhere into the list, I would like to get something, and when it's out of bound, then I would like to get nothing, which can be summarized using this commuting square. That's what I will call a coherent property. As a property I want to look up to hold for in this case. Okay, so if God forbid, but if you're a Coq user, you might just be thinking, oh well, that's very well. I will just write the lookup function. It's a good old NL function, so I can write in my proof assistant. And then, because I sinned and I didn't use the dependent types and all that stuff, then I will use tactics and I will prove a current theorem by banging at the proof goal and trying to knock these nasty dependent types away and get the proof to type check. So doing that, you will catch the potential bugs and stuff. But we feel that it's not optimal, especially in this case where we can actually use dependent types to do programming. And there has been a lot of that this morning, and that's another instance where instead of fighting dependent types, you could just program with dependent types. And so what we actually offer when you come to us and say I would like to implement the lookup function, which is a functional ornament of the comparison function, then we come back to you and say, oh, then don't implement lookup, don't prove its coherence, just implement that function instead, which is a dependently typed function. And what it does is says, well, given an m, natural number m, and given a list of size n, and the size, you have it into the type, right? So here you know it's a list of size n, then you should return something. So what is that something? Well, if n is less than n, then you must return something. You have no choice. The type tells you must return something. And if m is greater than n, then you must return nothing. So you see, intuitively, what we get here is that by construction, the function you're going to implement here is coherent. There is no way you can screw up, if I may. And actually, also, in this case, and in all the cases in our system, from that function, you can extract both the lookup function and its coherence proof. So it's not necessary, it's actually useless, it would be useless to write lookup and its coherence proof on the side. From that back, we can extract for you the coherence function, the lookup function and its coherence proof. So that's the kind of programming style we do in AXA, and I believe that this kind of programming style you would like to do in systems like Haskell, because you simply don't have proof inside Haskell. So this thing gives you a lookup function which is coherent, and it's automatically extracted from a nicely typed function. Okay, so imagine you believe me, and so you just go and implement high lookup. Well, you might complain because this function, the code here, is exactly the same code as the lookup function, which I was complaining about earlier. Well, it's not exactly, yes, the implementation is the same, just as this morning, we had a lot of functions which were the same, but the types were saying more. And these types are much more precise than the types of the lookup function. And the other thing, which is quite important, is that when you are implementing lookup, you as a human being know that on the side there is this coherence proof. So you're careful in your implementation not to screw up. Here, the computer knows what you are aiming at, And I'm going to show you that you actually don't need to implement that thing. You can play with the system and implement iLookup being helped by the system. Before doing that, I must digress. When I wrote this thing, I'm a member of the Church of Epigram, so I'm not allowed to do this sort of pattern matching things. I must use this type, which says when I'm defining m less than n, well, first thing I do is induction on n. And then there are two cases. If n is 0, then I can return false, I'm good. But if n is some successor of some number, then I do a case analysis on m. And if m is 0, then I return true. If m is a successor of some number, then I use my induction hypothesis to compute m less than n. So this way, you are always guaranteed that any function you define is structurally decreasing, so it's well funded. Right? So this has been promoted for a long time, and we are going to see another instance where this style is good for practical purposes. I should say before doing it really that this is all some sort of ideal syntax. We should perhaps discuss that later. But, so let's say I'm trying to give you some intuition of a process which happens in type theory. So I'm going to use a very nice syntax, which should then be elaborated to some type theory. This process of translating down to the type theory is not described anywhere. This is trying to convey some intuition. So here, when I'm defining iLookup, what I would like to say is, well, I don't want to duplicate this code over there, but I would like to say, I was doing induction on n, please do the same thing here. I said that here, I don't have a number, what I have is a vector. But because the computer knows that we are dealing with this object, and that guy has been computed from this number, from this definition here, we can actually tell the system, please lift the induction principle which was used before, and then we can compute the new induction principle. So when I say we can compute, that means the computer comes back to you and says, okay, I'm lifting the induction, and I'm doing it on vectors. And then it comes back to you and says, okay, there are two cases, nil and const. Right? Just as before we had 0 and successor, now we have nil and const. And next thing to do is the same for lifting the case analysis over there. And actually, in this case, we are also lifting a case analysis on a number, so we're good to go. So at this stage, what we have got is we have not duplicated. We have explained to the system to take the structure, which was in the definition of the comparison function, and lift it to the functional ornament side. And at this stage, what we have is all the recursive structure of the definition. Next step is constructors. So here, we were returning false. In this case, here, we need to return the functional ornament of false to the maybe ornament. And what it is, it's nothing. So if we ask the system, please lift, you add the constructor of false, now give me the lifting of that constructor, that will be nothing. And in that case, we don't have to do anything. It's already there. The computer figures out that this is the only possible solution to the problem. The next step is for true. No, we won't like to return. So what we want to return is the ornamented version of true to the maybe ornament. And what I said earlier is that we have ornamented true to this thing that says it's just an A. So the computer comes back to you and says, well, it must be just an A. I don't know which A. You tell me. But it's for sure, it must be just something. And so here you can give the A, and you're done. So again, this is fancy syntax. It's recording an interactive process. That is not implemented, but we strongly believe that something like that should work. And I hope it gives you the intuition behind the thing. What actually happened is that thing. But nobody wants. I mean, unless you're a disparate PhD running for your life, you wouldn't write this. I obviously did, but yeah, I wouldn't do that another time. So to conclude, well, with this system, we are hoping that, especially within different type language, we are hoping that we can start using these fancy data types we all love, with you know, index to enforce constraints and properties of your data types, and that should not cost you, you know, because the current state is that you have this data type, which is very imprecise, alignment, and then you start making it more precise, but then you have to take all its library function and re-implement it on the side here. With this lifting, which is in which you are helped to do the lifting, we are hoping that we can use more code across these ornaments. And doing so, we use the knowledge that is given by the ornaments to ask for the minimal necessary information to proceed to do that lifting. And another remark is with this constructing these very finely indexed types, like for iLookup. This style should let us do more programming, you know, programming with dependent types, and less time spent trying to verify code, and less time spent doing, you know, using tactics to prove things. To do all of that, we don't need much, actually. We just need standard type theory with a universe of descriptions, a coding system for data types, on top of which Conrad has shown how you can describe ornaments just as standard inductive types. And then in the paper, so we give a few universes to describe this sort of lifting from any simply typed function. So your base functions, the function you start from, will be simply typed functions. Then you can ornament them with any ornament you like. And we offer all that machinery I was describing in my example. So that means no crazy type theory, and every fancy syntax I was showing is not part of a TCB. We don't need to trust these things. They always generate these disgusting terms, which then the type checker will just check. The type checkers are happy with disgusting things so far. And that's it. So thank you for